Hello, everyone. Thank you for joining us for today's webinar. Today, we will discuss the use of satellite data in monitoring wildfire activity in the Arctic. The Arctic wildfires topic will be presented by our special guest, Dr. Thomas Smith, Associate Professor in Environmental Geography at the Department of Geography and Environment at the London School of Economics. Tom is a geographer and environmental scientist specializing in interdisciplinary approaches to understanding the role of biomass burning in the Earth system. So his presentation will be followed by questions and answer session. And to answer as many of your questions as possible, also Pierre Marcus and Grega Milczynski will be available towards the end of our session. So that would be all from my side. And now I give the floor to Tom.
So there's a reason why I have a burning forest behind me. This is from Banff National Park in Alberta, a little bit below the Arctic Circle, but I am a field scientist by nature. Most of my career I've spent measuring fires in the field, and that involves mostly measuring smoke from wildfires. And that's kind of important for the story that I'm going to tell today through this talk, because like many of us, I was locked down at the start of 2020. And at that time, fires were burning, well, raging through the Arctic Circle in the boreal forest of Siberia and up into the tundra region beyond the tree line as well. And having nothing to do for my research during 2020, I spent a lot of time using online satellite resources to kind of continue my passion for wildfires. And that's how I began getting interested in the fires that were burning inside the Arctic Circle. And really, it was a bit of a hobby during lockdown. This hasn't led to any kind of major research publication. I just wanted to share the results of my hobby as far and wide as possible. And I guess this talk is very much part of that sharing. I'll just start with what you're looking at here on the screen. I should add that there isn't a huge amount of Sentinel imagery in this talk, but what it shows is the importance of bringing together lots of different satellite products, from the really broad, moderate resolution or low resolution satellite measurements through to the high resolution that we can get from Sentinel as well, and show how Sentinel is very important for confirming some of the hypotheses that we're generating from these larger scale imagery products. So I'll just start with what we're having a look at here. So I call this the flame diagram on the bottom left. I kind of invented this during the lockdown. And what you can see here is a kind of unusual representation of fire activity. You've got fire activity on the y-axis, but we've got latitude on the x-axis, so going from 60 degrees to 72 degrees north. And in this animation, you can see the years piling on top of each other. This is the MODIS satellite record. So it begins in 2003 and ends in this diagram in 2020. And if you look generally below the Arctic Circle line, so to the left of that grey line, you can see fires building up every year on a kind of even, same sort of fire activity every year. But if you look to the right of that grey line, and particularly look at 68, 69 degrees north, you find that 2019, bang, bang, you've suddenly got a huge amount of activity, and the majority of fire activity at those latitudes occurred in those 2 years, 2019 and 2020. So that raises an important question as to whether that's a step change in fire activity at these latitudes. We don't know very much about what happened before the satellite record, so maybe this isn't particularly unusual and these were just 2 anomalous years. And these are really important questions that we're going to try and address in the talk. On the top right, you can see an animation of MODIS data from Terra and Aqua, NASA satellites. And it's important to emphasize here that these fires are huge, and we'll talk a little bit about the size of these fires. Every single one of the large fires that you see in this animation on top right here is roughly the size of Greater London, so larger than 10,000 hectares, larger than 100,000 hectares. These are mega fires. And I just want to thank, before I move on, the contributors to this talk, Mark Harrington in particular, for sharing a lot of the data that I've been using in these analyses, to Jessica McCarthy and Merit Turetsky for sharing ideas about the importance of what we were discovering during 2019 and 2020, and of course to Pierre Marcus as well, without whose imagery I think we wouldn't be able to answer some of the deeper and more important questions that I'm going to raise today. So let me move on. So the context is that 2019 and 2020 were unprecedented years in the satellite record. We can see an average cumulative fire activity here in black on this diagram here. We've got wildfire emissions of megatons of carbon, which is directly related to the amount of energy that these fires give off into space that is detected by satellites. And what we can see is 2019 was way above this average 2003 to 2019 mean. And I know this diagram isn't complete, but 2020 also yielded a very large carbon emissions and therefore fire activity. 2021, I'm not going to talk too much about beyond 2020, but 2021 was also a big fire, but most of those fires were a little bit further south in the boreal forest of 60 to 65 degrees north, with over 18 million hectares burnt in 2021. So these are some of the largest fires on Earth, and here we do have some Sentinel imagery here. So here's an animation of a very large fire at about 67 degrees north in the Sakha Republic. We can see 2 fires, then 3 fires, and then joining up to become, in this case, a fire that was well over 100,000 hectares, approaching 180,000 hectares, I think, this one. And I don't know if the slides will be shared with you afterwards. I hope they can be shared with all participants, but there are links to all of the imagery on each one of my slides if you want to explore these images further. So again, just a wider view here. This is June 2020, and this is the imagery taken from my opening slide. And just again, emphasizing that the larger fires here are all around about 100,000 hectares in area. What you can also see in this image is the kind of broader scale. You can see the forest to the south, which are the darker greens. And then as we move further north, the shades change to a kind of shade of yellowy kind of khaki color. And that would be the tundra region to the north of the boreal forest. And kind of in between, you've got a kind of mix of those 2 different ecosystems. And what we were seeing in 2019 and 2020 is a number of fires burning in the boreal forest, but also fires burning in the tundra ecosystem to the north. And we'll talk a little bit more about the importance of that later on. So given that we saw this unprecedented activity in 2019 and 2020, it raised a number of really important questions. There was a lot of hyperbole about fires in the Arctic, and that is the title of my talk. But really what we need to understand is what ecosystems are burning. So what is burning on the ground? Because the Arctic, depending on which longitude that you're at, depending on whether you're talking about Siberia or the Alaska or Canada, it's going to be very different. We have forest ecosystems, we have different types of forests, and we also have the tundra ecosystem. So we need to understand which one of those is burning and whether activity is anomalous in that particular ecosystem. Again, what type of forest? Is it large? Is it spruce? Are we looking at deciduous broadleaf forests? And a very important question that many researchers are actively interested in is whether these fires are burning on peatlands. Peat, carbon-rich soil, covers around about half of the land north of the Arctic Circle, and of course a very important store of carbon. And if this carbon is being activated, if it's decomposing because of the warmth from the fires, or if it's actively burning, then we're converting all of that long-term carbon store, which may have been stored for tens of thousands of years or longer, into atmospheric carbon dioxide, which is then available to drive climate change. Another question that's important to address with these Arctic fires is whether the fires are burning on permafrost soils, and also what type of permafrost. Is it high content, high ice content? Is it low ice content? Is it discontinuous or continuous? All of these very important questions to assess the impact that these fires are having, especially given the unprecedented activity in those years. And so to do this, I kind of brought together a lot of different data sets, including land cover data sets, state-of-the-art land cover data sets, as well as very new maps of peat carbon that came out around about the same time that I was doing this analysis in 2020, and also data sets on permafrost cover to kind of try and correlate, or at least map on where these fires are occurring, and then trying to get a better understanding of what is lying underneath these fires, what is burning, what is the soil type, what is the permafrost condition, to try and answer some of these deeper questions about the fire activity in the Arctic. So the first important question to ask is, and I like this term invasion because it was coined about 14 years ago now in a paper that investigated what fire activity would look like by around about now, 2010 to 2039, and then later on this century. And if we have a look at the current period of time, this is a forecast for I guess 3 decades, 2010s, 20s and 30s, according to this paper that was published in 2009 by Meg Krawczyk et al. In PLOS One. And what we see is that there are places here that, according to their ecological and climate modeling, would see an invasion of fire activity come the current time. I guess 2020 lies in the middle of this time period. And interestingly, we see that those orange shades that indicate an invasion occur mostly in the eastern portion or in the eastern hemisphere. So we're looking at Scandinavia and most of Siberia with these orange dots here. And that was exactly what we saw during the 2019 and 2020 fire seasons, with fires burning further north in these regions that had been predicted in this paper in 2009. So we might be able to call this an invasion. To assess the land cover, using this land cover data set here, you can see just some kind of zoom ins. We've got different tree cover types here, shrub cover to the north, and then we've got tree cover to the south, including your broadleaf deciduous, as well as needle-leaf deciduous and needle-leaf evergreen here as major land cover types. Here's kind of eastern Siberia, central Siberia, and we've got the Alaskan Peninsula here as well. And what these maps are showing, we're going to have a look at a few of these, is the kind of burgundy dots of all fires in the MODIS record from 2003 to 2020. And then the red fires in this example are just the fires burning in 2020. So you can see the extent of fires in 2020 quite significant compared to the full record going back to 2003, particularly in the eastern Siberian region that we're looking at on the right-hand side here. So the data set is from Copernicus, so it is from the EU, but it's based on total FRP observations from MODIS, the NASA satellites, and thanks to Mark Parrington for providing this. Again, the beige spots here are the full data set, and these are all fires north of 60 degrees north for May to August 2003 to 2020, and the red spots, just for example, are in the 2020 fire season. Again, highlighting the importance of Siberia, not a great amount of activity in Canada and Alaska, and highlighting the scale here, where a lot of the fires were covering a huge area compared to the previous years. Again, just to have a closer look at that diagram that you saw at the start, the animation, the flame animation. Again, you can see the relative contribution of 2019 and 2020 to the 18-year record at these high latitudes, especially north of 68 degrees north. You can see that here that almost all of the fire activity occurred in 2019 and 2020, whereas where we look further south, there's more of an even relationship between the years. So again, this kind of indicates the fact, a possibility that these fires are quite unusual at this latitude, and potentially that invasion that was forecast by Krawczyk et al. In 2009. So just again, have a look at that latitude in this animation here. The final 2 years showing quite significant activity at those high latitudes. Just a little bit on 2021, but again, if we look at May to July, most of these fires occurring further south, and there was less fire activity in the Arctic Circle in 2021. So if we look at fires by land cover, we've got 2 stories to tell here. We've got the full season inside the Arctic Circle on the left. The grey bar here, which is the majority of the burnt area, is the needle-leaf deciduous, so potentially the spruce and larch forest. And what you can see here, this is the full fire season, May to August, and 2019 and 2020 being anomalous years, or more than double. And on the right, we've got the second story, which is the early fire season in the tundra. So this is just May to June. And what we're seeing as well is that, and this was quite apparent in both 2019 and 2020, was that in the early part of the burn season, we were seeing fires very far north when you wouldn't normally expect to see them, which suggests that, one, the vegetation at these latitudes, so this is beyond the tree line, so this is almost certainly permanently frozen ground, permafrost. We're looking at shrubby type vegetation or stunted trees in the tundra, but normally this should be frozen and then boggy and very wet in the early part of the burn season, and yet again 2019 2020 standing out as having particularly high amount of fire activity in these earlier months of the season, suggesting that the tundra is drying out earlier on in the summer than it would have done in previous years. So two really important kind of insights into what's happening at these high latitudes. And here we have some Sentinel imagery from Pierre Marcuse. Sent this over to me when he knew I was giving this talk. But these are fires burning in the boreal forest, so to the south of the tree line. And we're going to have a look at some close-ups of fires burning in the tundra a little bit later on. But we can see here, and what's quite important is the intensity of the fires. We can see that the fires are driving very high plumes into the atmosphere. We can see the convective energy with the plumes almost generating their own clouds in some cases. Very high intensity fire radiative power as reflected by the brightness of the yellows and the oranges in this kind of false color imagery here. Suggesting that we've got these high intensity fires, and this kind of raises a question as to the severity or the damage that these fires are causing on the ground. And we'll come back to that at the end of the talk when I kind of try and explain what the impacts might be on the ecosystems and whether we will see a forest replaced in these places or whether we could expect to see some form of ecosystem change. So this is a very important paper that came out in 2022. Thank you to David Gavot, who kind of sent me this paper again when he realized I was giving this talk, Descartes et al. Because what they do is take the analysis further back in time. And what we can see here is a multitude of different fire records that all show essentially that 2019 and 2020 were highly anomalous years. And as we are going back into the 1980s now, we can see that the climatology, we're looking at a 30-year period, more than a 30-year period, suggesting that not only are these years anomalous, but this is probably an indicator of some form of step change in the record. And we'll come on to talking about peatlands, which is the second plate on this figure in the next section of the talk. So we had invasions, but do we have a zombie invasion? I can't help but use this terminology, but let's have a look at what we mean by a zombie fire to start with. On the right-hand side here, we've got kind of an animation thanks to the people who are involved in a nature paper I was involved with, Merit Turetsky and Jessica McCarty. What you can see here is a fire burning on the surface that gets into the peat. That fire may be put out by the rain or by human activity, but the fire continues to burn under the surface. And then we have the snowfall over the winter, but the fire continues to rage. And during the next burn season, the fire comes to the surface. Now, it's very difficult to assess this using any form of satellite imagery as to whether this is occurring, because you need to have observations on the ground really to confirm a fire re-emerging from below the surface. But zombie fires potentially could play a very important role in feedback loops. So the more likely these are to happen, the more likely we are to see ignitions in the following season and so forth. Through time, that could lead to a kind of runaway snowball effect with these Arctic fires and peatlands. But perhaps more importantly is just assessing whether these fires are occurring on peat or not, let alone the question as to whether zombie fires exist. There have been some papers on zombie fires. This is an abstract from the EGU in 2020, showing some evidence using both on the ground kind of reconnaissance as well as satellite imagery to investigate fires that were burning in one season. So this is September 2015, and then burning the following year in May 2016, looking at fires that burned in one season and then continued to burn in the following season, suggesting that potentially the fires in the following season were ignited by these underground fires in the previous burn season. However, it is very, very difficult to assess this using satellite imagery alone. And at the moment, it's beyond really the capabilities of most of our products. So this was April 2020, so well and truly locked down as far as the pandemic was concerned here in London. And there was this kind of astonishing amount of fire activity in this region of Siberia. You can still see it covered mostly by snow and also cloud cover here. And as the snow melts, you've got the emerging fires. You can see the red dots mostly in the kind of valley regions of this imagery here. So it begs the question as to whether these are zombies, but there's absolutely no way we can tell whether these were ignited by fires in previous seasons. You could look to see whether there were fires burning at the end of the previous fire season, but it's quite difficult to pick up even kind of medium-sized fires at the end of the season, especially once cloud cover becomes an issue. Or whether these fires were simply started by humans to clear the land for some kind of agriculture early on in the growth season. But anyway, it poses the question, are these zombie fires? And Twitter became very important with engaging with this issue during the lockdown. So it took off as a major kind of topic of discussion in New Scientist and National Geographic once people began to really investigate what was happening at these high latitudes and whether some of these fires were ignited earlier on in the previous burn season. But to continue just talking about peat, because peat is very important. I do a lot of my research on peatland fires in the tropical regions. And so I was very keen to understand, how many of these fires or the extent to which these fires were burning on peatlands. And this is a peatland map from Yu et al. That was published in 2020 and freely available online. You can see the hatched areas here are the areas of peatland. And ultimately, it's quite clear that many of the fires were burning on peat. And have a closer look at that. This is the distribution of fires again in May to August on the left, and then just the early part of the dry season in beyond the tundra in the tree line on the right. And once again, we can see that as well as being anomalous years 2019 and 2020, around about half of the fire activity is burning on areas that would be classified as peat, according to this peat map. Now, an important thing to emphasize, because I've seen someone already asking about this in the chat, is the accuracy of these underlying spatial data sets on land cover and peatlands. And ultimately, the accuracy is not particularly great. Land cover data sets are notorious for having inaccuracies. And so are these peatland data sets as well. In some places that they simply haven't been mapped. They tend to be based on survey data rather than satellite data, because once again, it is really difficult to tell where peatlands are, and particularly the kind of carbon content of those peatlands from satellite data sets. So we always have to take some of this with a pinch of salt. I updated this analysis using a 2020 map of peatlands from Hugelius et al. And this map not only shows the location of peatlands, but also includes the soil organic carbon, so the kind of density of carbon in those peatlands, which again enables you to investigate whether these fires are occurring in particularly carbon-rich peatlands. So if we have a look at the next slide, what we can see here is the shades of the bars here. These are fires that are only occurring on peatlands, so fires delineated by the peat map. And the kind of shade of grey here is the intensity of the carbon, or the carbon content, both in terms of the peat depth. So again, the deeper the peat, the more carbon it's likely to contain, and the kind of soil organic carbon content as well. So there was some speculation as well at the time that the fires through time, i.e. through the last kind of 30, 40 years, are moving on to deeper peat regions, because the deeper peat regions tend to be waterlogged, and the edges of the peat domes are the first to dry out when it comes to changing climate and a warmer climate, which this region is experiencing. It is heating up faster than the rest of the planet. So there was a potential that we could use this data set to investigate fire encroachment onto peatlands by using the distance from the peatland edge. That hasn't been done yet. There's an opportunity there if anyone wants to get a paper published, I think. But it seems to be that there isn't really a pattern here in fires moving onto deeper peat. So we would probably see a change in the colour of these bars if the fires were moving into deeper peat areas, but instead it's sort of random. So at the moment, we're seeing fires all over the place when it comes to these when it comes to peatland encroachment. But an important question to ask is whether the peat is burning. So peat fires are very different to flaming fires. On the left, you've got an example of a flaming fire. On the right, you've got an example of a peat fire. And the main difference is the persistence. So the peat fires can persist for weeks, sometimes months. And they have very weak fire plumes. They produce different color smoke, and they burn downwards as well as laterally. And so again, this is quite difficult to sense from space, but here we've got kind of on the ground footage of a peatland fire on the top right. On the bottom left, the video is not quite working, but you can see a flaming fire in a conifer stand. Very, very different fire behavior between these two types. And it's very easy to spot this on the ground from ground measurements, but it's quite difficult to sense this from space. We'll come on to the reason why in a minute. So anyway, again, I was sharing this as I was doing the analysis back in 2020. It picked up a lot of attention on Twitter, and that included from the likes of Merritt and Jessica in the States, who I'd never worked with before, but we worked together on trying to address what the key questions were about these fires. So we published kind of an opinion piece in 2020 that set the scene for what we thought were the most important questions. And whilst we could, demonstrate evidence that fires were burning on peat soils, it's very difficult to take that big data analysis and assess just how much of those fires, if they're burning on peat, but are they burning into the peat, is a really important question that I think no one has really answered yet. And that is one of the key questions going into the future when it comes to these fires at high latitudes, is just how much peat is being affected. In this paper, we've got this nice Sentinel image here, which Pierre Marcuse provided to us. And what we can see is the active fire here on the top right. But if you look closely, and I'm not too sure how well this is going to be come across when it's shared, but there is residual peat smouldering. You can see some kind of thermal signatures in this false color image on what would have been a fire on previous days or even weeks beforehand, demonstrating that the fire is persisting here and suggesting that there is a peat fire. But it's very difficult, one, to tell how deep these fires are burning and therefore how much carbon is going up in smoke. And two, we're only seeing little snippets from these thermal anomalies, whereas actually there's probably a wider amount of land on fire. You can kind of see that from the fact that there is smoke appearing to come from this land, but no evidence of thermal anomalies. So really important question in fire science. And there's many reasons why peat fires are hard to detect. In many cases, the fire is occurring below the canopy cover at a lower temperature. Sometimes there's ash and debris covering the active fire. The fire can spread underground and often will persist for weeks when the clouds might roll over. And again, very difficult to detect these fires under those conditions. Here's another really nice Sentinel image from Pierre. Again, what you can see is the head fire at the top of this image to the north, but you've got backing fires at the bottom of the image, just little specks of red left behind thermal anomalies. But in all cases, these are likely to be burning into the peat soil in this image. Again, these were persistent for a number of days when you check the imagery. So again, we know that these fires are burning on peat, in some cases burning into peat, but at the moment it's impossible to tell how much peat is being consumed. Further evidence comes from photographs on the ground. So these are photographs taken by Greenpeace at the fires in 2020. Someone who goes to peat fires very often, this is very clear evidence of peat fire. You can see there's no active flaming on top of the surface here. Instead, you've got the smoke kind of billowing out like mist from the ground, very similar to that video that I showed you from a fire in Malaysia. Totally different ecosystem, but very similar fire behavior. And this is all evidence that points to the fact that these fires are burning into the peat soil. So going back to this paper in Science, which I think is fantastic, it goes back to the early 1980s. Again, they use a similar peatland data set to assess whether these fires are burning in carbon-rich peatlands. Again, they can't say for certain whether this fire is burning the peat itself, but we know that the fire is burning on the carbon-rich peatlands. And again, this paper also suggesting that 2019 and 2020 in the 40-year record are anomalous years, which corresponds to my analysis, again suggesting these 2 years, if we look at the brown shades on these bar charts here, are quite unusual. Interesting, my analysis also points to 2013 being an important year like theirs does as well. So it's nice to have some corroboration between the two different analyses. As far as permafrost is concerned, I won't touch on this too much because the story is pretty obvious. Most of these fires are burning on continuous permafrost, so that's 90 to 100% permafrost color. That's the pink shades here. If we look at ice content, well, most of these fires are burning on high ice content as well. It's a pretty boring story, really. And if we look at the full season inside the Arctic Circle, this just shows us that in 2020, it was all on continuous permafrost, and most of that in high ice content permafrost here. And in the tundra as well, it's a very similar story. So we've got these high latitude fires, almost all of them burning in the tundra. So I plan to talk for about 40 minutes. So I've got about 8 minutes left to talk about climate change and what the climate change wildfire feedbacks involve. When we talk about climate change and it's really useful to talk about pyrogeography, or the ecology of fire. And there are 3 factors that we can use to describe the distribution and abundance of fires. And it's very similar to the ecology of organisms like trees. So when it comes to organisms, when it comes to ecology, you need resources and you need physiologically appropriate conditions, and you need the ability for those organisms to disperse and spread. For fires, it's very similar. The resource is the flammable vegetation. The physiological appropriate conditions are fire-conducive weather patterns, and the climate and the dispersal ability, i.e. the ability to spread, involves ignitions. And that is what determines the geography of fire on our planet. When you have all 3 of these, then you tend to have fire activity, which is what's mapped out here below. We can see here that as we move to higher latitudes, generally the fire-conducive weather patterns tend to take over because it's too cold or generally too wet and moist and damp for fires to burn in the summer at the highest of latitudes. But as we've seen, we're beginning to see an invasion further north as things are getting drier and warmer. If we think specifically about fire, it's quite complicated. It's not just about the weather. People think it's just going to be down to temperature and humidity, but vegetation and fuel availability are very important as well. We're getting more atmospheric CO2, which causes plants to grow faster, and we're getting changes in moisture throughout the year, which can change the amount of vegetation on the ground. Generally, at the higher latitudes, we're seeing a longer growing season, for example, which potentially leads to more fuel availability on the ground. Obviously, temperature, rainfall, humidity, and wind, important for the weather. We also need to consider how climate change is going to affect ignitions as well, although most ignitions on our planet are caused by humans. Now, there's a very strong relationship between how fires spread and the climate, or the weather, or the fire weather. In this case, what we've got here is a correlation between a Canadian fire weather index called the initial spread index. And this is very appropriate for the boreal forest, for example, at these high latitudes. If we look at boreal spruce or boreal mixed wood, what we see here is the relationship between the rate of spread and the initial spread index, which is a function of temperature, relative humidity, wind, rain, and particularly wind on the day of a fire, is quite linear. So the more fire conducive weather you have, the greater the rate of spread of the fire. But what this means is when it comes to the area that burns on the ground, you get an exponential relationship between these fire weather indices and the area on the ground. If it's a linear fire spread relationship, well, it's an exponential fire area relationship. And what's really interesting about this hypothesis is that it's confirmed by that 2022 science paper, as we'll see in a minute. But again, this is from Copernicus data. Here we've got anomalies of soil moisture during 2019 and 2020, just emphasizing that things were very unusually dry during these years, and that the lowest kind of soil moisture, or the greatest soil moisture anomaly, I should say, where 30–40% below usual, was associated with the areas of greatest fire activity during those years. This is from that 2022 paper. I think this is fascinating because we've got various fire weather variables and fire fuel variables, as well as ignitions on this plot, all of those relevant to climate change and relevant to the rate of spread of a fire, as I showed you with that diagram earlier. Air temperatures, vapor pressure deficit, which related to relative humidity, the growth of vegetation on the ground, NDVI, and the number of ignitions, all showing a trend through, and these are significant trends, at least for the temperature, humidity, and NDVI, all showing a trend through the past 40 years in Siberia and Arctic. And naturally, if we look at the burnt area, we have this rather stark and worrying exponential relationship between these important kind of fire weather variables, humidity, air temperature, the amount of fuel on the ground, and the number of ignitions, all showing a significant relationship and a significant exponential relationship, which is what you'd expect according to that relationship between rate of spread and some of these fire weather variables that I showed earlier. So this kind of bodes this is, I suppose, a little bit gloomy for the future, because if we look towards 2100, this is the forecast from that Crawcher et al. Paper, which had already suggested there would be an invasion at high latitudes in the current decades. But we can see that that is likely to continue for most of the Arctic region in Siberia, as well as the edges of Alaska and potentially in Greenland as well, and on the edges of Greenland later on this century. And this paper goes one step further, the paper in Science. I've shown you a few figures from this paper, extending the forecast into the future using two different climate change scenarios. And what we see here is the year 2020, which was once a kind of completely unusual and was probably never going to happen in the earlier parts of the century, 1960s to 2000s, very unlikely to happen at all, maybe a 1 in 1,000 year event. By 2020, we're looking at something happening every kind of 10 to 20 years or so, and becoming far more frequent, almost every other year by the end of the century, or in every year if we consider the kind of more extreme climate scenario, the RCP 8.5. So a couple of important questions to finish on, and this is where I think Sentinel can really play a role, because you need to have a much higher resolution understanding of what's going on the ground. But will the forests grow back? Has there been a change in wildfire regime? We need to understand what the stand replacement frequency is. We also need to understand something about how intense the fire has been and what is growing back in its place. What's happening to the more fire-prone tundra ecosystem further north? These are important questions, because if this is the case, if these extreme fire years, like what happened in 2020, become commonplace, it means that the stand replacement frequency is going to be much greater. Instead of there being a fire every 100, 130 years in a particular place, we're likely to see fires every 10 years, or even more frequent in many places in the Arctic, which means that the forests are not going to grow back. They'll be replaced by a different ecosystem, and we have a net release of carbon to the atmosphere as those forests are replaced by lower carbon intensity ecosystems. So if we consider maybe the boreal forest to be in the middle of this diagram here, once we have frequent fires, it kind of pushes the ecosystem to be either scrub or a non-forest like a grassland. And as we move to the right of this diagram, we move from a carbon intensive, where the carbon's stored in the biosphere, to a less carbon intensive ecosystem where the carbon's stored in the atmosphere. And this, of course, can lead to positive feedbacks, whereby the extra carbon in the atmosphere drives further warming and therefore drives further fires at these high latitudes, which seem to be very sensitive to changes in temperature, relative humidity, and the amount of fuel on the ground. Some open questions really is, is peat on fire? We simply can't answer that question. There's some evidence in the Sentinel imagery, but it's very difficult to automatically detect this. Is this a significant driver of permafrost thaw, or just an isolated phenomenon? What do the fires on permafrost even mean? Are the fires burning into the peat going to reduce the insulation that peat provides for the ice further below, and therefore drive further melting of the permafrost, and therefore releasing greenhouse gases into the atmosphere? Or is it some other form of geomorphological agent? These are really open questions when it comes to these fires, and every single one of these could be a paper or even a PhD, I think, as far as the scope of these questions. And finally, we know that these fires are releasing huge amounts of black carbon into the atmosphere in the form of particulate matter, or the soot in the smoke. And again, we need to understand how significant this is. Are we going to see a black carbon on snow effect, where the carbon lands on the light colored snow or the sea ice in the Arctic region and cause it to melt because it causes it to be darker and absorb more sunlight? Or does the smoke in the atmosphere help to shade the Arctic and therefore lead to a cooling effect, which might be a form of negative feedback at these high latitudes? Here we just got some more Copernicus evidence, 2019 and 2020 anomaly. This is in black carbon emissions in micrograms per meter cube, just showing that these 2 years were big years for pumping huge amounts of this pollutant or black carbon soot into the atmosphere. Anyway, that's it, I think. I just want to plug this paper because this is where we raise some of these important questions. And really, it's a significant MMM problem. That stands for monitoring, modeling, and management problem. It's not just about the monitoring and the modeling, but also what's going on the ground, because many of these fires are probably associated with human activity. But again, we don't have a great understanding of whether this is happening on peat. We don't really understand what it's doing to the permafrost, and we don't know why these fires are happening in the first place, which means we need to have an interdisciplinary approach to solving this challenging problem, which seems to be kind of running away from us at the moment with these exponential relationships that are associated with climate change. So that's it. And I look forward to your questions. Thank you very much.
Thank you, Tom, for this really great, detailed, and very informative presentation. Like you said, we can proceed with questions and first review the questions already asked in the chat. So there was the first question before, actually more of a request. Can you comment about long-range forecast wildfires areas, for example, 50, 100 years?
Yeah, so I think you always have to take wildfire forecasts with a pinch of salt, because one of the most important factors is human activity on the ground. So we can forecast changes in fire weather because we have quite reliable climate models that tell us what the temperature is going to be, and temperature is very important. Although precipitation is less reliable, but generally in these regions we're not expecting to see a huge change in precipitation because they're quite continental in nature. So as far as the fire weather projections are concerned, we're quite confident in those projections, but it's the other things that matter when it comes to what fire behavior on the ground. One is the fuel. It's difficult to predict fuel changes. Now, the Krawchuk et al. Paper tried to do that. They have an ecological model that assesses how much fuel is going to be available on the ground. But I think there are always going to be high uncertainties with that. One, because we don't know what the feedback effects are going to look like. Whether there will even be a forest there by the end of this century is a really good question, because if we have frequent fires over the next 30, 40 years, then we're not going to see the regrowth of boreal forests in many regions. So that's an open question that I don't think that's built into many of these projections. The other problem is ignitions. So ignitions are a real wild card, because a lot of these ignitions are probably caused by human activity, either purposeful or inadvertently. I suspect that very few of these fires are started naturally by lightning. And again, it's very difficult to tell from satellite imagery the cause of these fires. And so, with those two uncertainties, it is very difficult to project into the future. But both Krawchuk and this science paper from 2022 attempt to do this. But I think a lot of that is relying on the changes in the climate, and probably having the ecosystem, the fuels on the ground and ignitions as static. So you just have to take these with a pinch of salt. But either way, the relationships are very clear. A warmer environment, and things are warming up much faster in this region than everywhere else, leads to a linear change in the rate of spread of a fire, and a linear change in the rate of spread of the fire relates to an exponential change in the area. And that is what we've already seen in the past data, which is quite evident in this science paper, and we can expect to see going forward as well, I think.
There was another question from Mohammed. He was asking, can we use open flame fire detection algorithms for smoldering fire type? And if you have any recommendations that can be given to use EO for such fire detection and monitoring, especially considering peat and coal fire?
Yeah, it's a great question. I kind of have to qualify myself here. I'm not a massive satellite remote sensing person, so I don't have all the knowledge on this topic, but I think I can give a good answer to this, because I know it's a very important question. I work with smoldering combustion scientists who mostly are concerned with modeling smoldering combustion on the ground. They're engineers, team based at Imperial College London. At the moment, there is no kind of algorithm or product that works for smoldering fires. It's very, very difficult to, one, distinguish flaming fires from smoldering fires, but also to detect smoldering fires in the first place. There's a team at King's College London who are working on this, led by Martin Worcester, and I believe their algorithm is based on nighttime observations. So a lot of flaming fires tend to die down at night, or be put out entirely at night because of the high humidity conditions, but the smoldering fires will continue. So I believe there's an algorithm that is being developed that is using nighttime observations of the thermal energy given off from fires, if that makes sense, to try and kind of distinguish between the two types of fire activity. I don't know if anyone else, Pierre, you've kind of unmuted yourself, so I don't know if you have anything to say on this.
Well, the answer really is yes and no. It really depends on the size of the fire and how deep it is. The more cover you have, especially if there's snow cover, which makes it really hard. I believe satellites are still a few generations away from reliably detecting peat fires, especially deep underground, but drones might be helpful.
Yeah, I think this is definitely an opportunity for aerial remote sensing and good old-fashioned surveys on the ground, but there's no way you can cover. You're not going to be able to get the data that a satellite product gives you from either drones or on-the-ground surveys. So this is a really important open question and a huge opportunity, I think.
Thank you both for this one. Susan, let's try one more time. You will be able to unmute yourself now.
I can. Thank you. Tom, I just wanted to say thanks for a really interesting presentation. Great work and a lot of challenges ahead for doing a better job of defining especially the role of peat fires, I think, and the feedbacks to carbon cycle. And then some of the changes in vegetation, which we're already seeing in the southern part of Russia, pretty strongly, but not so much in the north yet.
Yeah, Susan, I think thank you for your comments. I think the major kind of update, which is not thanks to me at all, but thanks to this team with their science paper, and I can see David Gavo is on the chat here, but that I couldn't believe it when I saw the exponential relationship, because this is exactly what we were expecting. We see it elsewhere, we see it in California, we're seeing it in the United Kingdom now, and we've seen it in Australia in the past, is that as temperatures warm, you have this linear relationship, very clear linear relationship between rate of spread, but then that leads to exponential change in what you see in terms of burnt area. And I think it's very clear in that paper that they've established that now. So it's a very important step forward, but also a kind of scary one.
Andres was asking, how accurate do you expect the vegetation cover to be? Is it based on local field data or remote sensing? And probably this could influence your results on the vegetation types that are most affected, right?
Yeah, and my analysis is very basic. It's probably why I've never managed to, well, I haven't even tried to publish this, but that's probably one of the reasons why. I think really it was just supposed to be there as an indicator to try and mainly determine the difference between fires that were burning in trees and fires that were burning in scrub, as a kind of good delineator between forest and tundra. The data set I'm using is very old, mainly because of the limits in computer power. All of this was done on my laptop. And as I say, it was a hobby during the lockdown. I didn't have access to any kind of high-powered computing. Yeah, my answer is it's not particularly accurate, and really it was just using it as an indicator. And land cover maps are not great. It's much better to use localized ones, regionalized ones. Susan knows all about that. But for this global analysis, I chose to use a global land cover data set, but it's old, and although it has been ground truthed, I would still say the accuracy is not great. So yeah, it's good to point that out, basically. Similar with the peat mapping as well.
Thank you. Then we move to Pavan's question. He was saying that we know that there are wildfires and use MBR indices to check in on the damage, but can we also use Sentinel 5P and check the atmospheric effect due to Arctic fires during that time frame, and check also the time lapses and also the extent of the area likewise?
Yeah, so I think the opportunities for Sentinel here, I guess this is a question about what can Sentinel add and what can follow-up studies of these fires help with. So yeah, NBR, so for those who don't know what that is, that's the normalized burn ratio. So it's used quite frequently to assess the severity of a fire post-fire. So looking at recovery following, the year following, or you look at 2 different years to assess the severity of the fire. I think that's going to be important, and I don't know of anyone that has done that yet for the 2019-2020 fires, because I suspect they burnt with a different intensity, because again, this 2022 science paper shows the relationship between the fire weather indices and the area that burns, but also what we should expect is a relationship between the intensity of the fire and those fire weather indices. So we'd expect to see more energy given off And that should translate into a more severe burn on the ground when it comes to the damage, and whether we expect to see a recovery or not, or a change in the ecosystem. So I think there's one important follow-up study that could be done there using things like the normalized burn ratio. I'm not too sure about the atmospheric effect that's mentioned in the question, but I think important questions around peat fires, so looking at the persistence of these hotspots through time for certain case study fires is something that Sentinel could do, where you revisit a fire as it's active and you keep going back to the site to see if there's any smoke, so any atmospheric effect, or whether there's still some kind of thermal signature that is there a week or 2 weeks or 3 weeks after the main fire has come through. And finally, looking at the geomorphology, looking at what happens to land on permafrost. Do we see new depressions? Do we see new ponds forming in places that had experienced fires? Because that would suggest that there had been significant impact on the ice below the surface. And I think that would be a really interesting follow-up study that could only use high-resolution satellite imagery, such as that from Sentinel. So I think there's a big opportunity there as well for some interesting science to be done on post-fire morphology associated with changes in the permafrost in these regions.
Then we had a question from Lillian. She asked, how come the predictions for increase of wildfires is so high in inland Greenland? So this was related to the slide with end of the century predictions.
Yeah, I think that's some form of anomaly in that paper. I don't know the team of that paper very well. We do not expect Greenland to be melted by the end of the century. So I think that is probably ignoring the fact that there's a big ice sheet on the top of Greenland when it comes to those predictions. However, in the peripheral regions of Greenland, where there is vegetation, where there is stuff to burn, I would say those predictions are valid. And we're already seeing that. We've seen unprecedented fires in Greenland in the recent decade or so. But I believe their model probably ignores the fact that there is an ice sheet on Greenland. So you can kind of ignore that inland red Greenland signature. Similarly, you'll see coloured areas for the deserts of our planet. Now, in some cases, that is a real increase because we might see the greening of those deserts. So the Tibetan Plateau, even the Sahara has projections that by the end of this century, it could be grassland, could be green rather than barren rock or barren sand. And that would definitely translate into an increase in fire activity. But as far as Greenland is concerned, I'm pretty sure there'll be an ice sheet there at the end of the century, although a melting one probably.
The next question is regarding the activity of bad fires during winter. Could we expect some pollutant signals to guide us to map them?
That's a really interesting question because I've actually done some work on this. My work has showed that fires that burn deep underground or have a deep layer of ash that cover the active burning surface actually have most of their pollutants filtered out when it comes to the particulate matter anyway. So you would potentially not see a massive particulate matter signature from these fires, because if you imagine the fire's burning underground and the smoke is emanating, but it's having to travel through pores in the ash or pores in the soil to get out onto the surface. And what we find in looking at fires in the tropics is that most of the particulate matter gets stuck on its way out, and so it gets filtered. So by the time the smoke, or by the time the product of the combustion gets to the surface, all that's left is the gases. So it's potentially very difficult to pick up these smouldering fires looking at particulate matter only. But we should expect to see carbon monoxide anomalies. But the scale of the carbon monoxide anomaly, especially if you're using a satellite to look at carbon monoxide, is probably going to be quite difficult to detect at the current kind of sensitivities of satellites for looking at gases in the atmosphere. So the answer really is at the moment it's not possible. I think, again, as Pierre suggests, detecting these fires is probably not even the next generation of satellites, probably a few generations of satellites away before we have satellites that are sensitive enough to these small changes in gas concentrations. And when I say small, when you're talking about the whole atmospheric column, they're relatively small. And as far as particulates are concerned, I do think that once they get deep, and once we're talking about these overwintering fires, a lot of the particulates don't actually make their way out of the ground because they get stuck on the way in a kind of filtering effect.
Kirsten was asking, is there a Sentinel 5P product that could be useful for smouldering fires?
I think there's a simple answer to that question, and that's no. There are no products currently for smouldering fires. I don't know if Pierre wants to come in on this, but I think the best way of looking at smouldering fires is actually to use the visible, the visible imagery, and to use true color composites that incorporate some of the thermal bands, and look closely at some of these fires to see what happens after the main fire comes through. And at the moment, it's very much a manual approach to trying to understand whether any of these fires are still burning or persistently burning. That's what you want to look for. You want to look for persistent smouldering after the
Indeed.
main.
Look.
Yeah.
Sorry.
Oh, sorry. Carry on, Pierre, because I think you might
Indeed,
have a good answer.
looking for smoke and IR signatures. I don't really see how a Sentinel 5P could be helpful at the moment. It's just not enough. There's just not enough signal.
Yeah, I agree. The resolution is too low, and at the moment, I think you need to be using the 10-meter products to try and manually assess whether these fires are persisting or not. At the moment, that's all we can do, and that's all we were able to do in our Nature Geoscience paper as well, to say, look, here's an example. We think this is still smouldering. We can't even say for sure whether it's still smouldering, but there is some evidence here that these fires are burning into the peat, and combined with the photos, from news crews on the ground, we can confirm that there's definitely peat fires, but we just don't know the extent. And that's such an important question to answer, but we're not there yet.
Thank you both for this one. I had a feeling, Tom, did you want to say something else as well? I think we came till the end of the questions.
Yeah, I just share one more thing. So I've just posted it in the chat. This is not publicly available, but I'm happy to share it with people who've come to the talk. I'm just going to see if I can show you what this does. Yes, so here we go. So I shared the link to this. This is basically an interactive tool. So all of the data that I presented, land cover, peat, FRP on permafrost. So this is, I'm always using the FRP, which is just the fire activity, the amount of energy that these fires give off, rather than area. And again, you can interrogate this by looking inside the Arctic Circle, whether you want to go above the tree line or below the tree line. I can switch this off and all of these should change. Just wait a second. Oh, my connection's lost with Tableau. I'll just refresh that. Okay, welcome back. I'll just turn off above tree line. And hopefully, yeah, all these figures change when I change that. We can also confine by latitude, so we could just look at the highest latitudes. So I could just look at 68 degrees north or above, and again, suddenly all of the data in the earlier years disappears, because we're only really seeing fires in 2019 and 2020 at the highest of latitudes. We can confine by Siberia, so we could just look at kind of 50 to 180 degrees east, although that doesn't make a huge change with that data set, because most of these fires are in Siberia. We can just select different years. You can filter by month, so if you only want to look at May and June, you can do that. It's all kind of built into this interactive dashboard, which I've shared on the chat. Okay.
Susan, one last word from your side as well. You raised your hand.
Yes, one of the things that doesn't get talked about very much is that a large number of the fires in Siberia are surface fires under a canopy, and these are much harder to detect. And certainly if you're making estimates of radiation from the fire, it's muted, because a lot of the radiation gets absorbed by the canopy instead of showing through it. And this is especially true with pine forests and some of the large forests. Do you have a comment on that?
Yeah, it's a good point. I think surface fires are fairly well picked up still through the canopy cover with some of these products, but it's still a very good point. The paper in Science, Descartes and with David Gavo, who's also in this chat, I mean, they're using burnt area data sets. So again, despite them being surface fires, I'm not too sure how reliable the burnt area data sets are either, because again, you've got canopy cover that might hide the surface fires underneath. So I think in both assessments, whether you're using FRP or burnt area, there's going to be some bias against these surface fires. But I guess the surface fires are less important when it comes to assessing the ecosystem damage. It's the huge, big, intense fires that are going to wipe out the trees, the ones that we should be looking at. So if we're looking at trends, then it still doesn't bode well. But yeah, you're right. We're probably missing some of these fires, and we know both the burnt area products and the FRP products work less well in forested, especially continuous forest conditions. So another kind of data set that you need to take with a pinch of salt, and there isn't much we can do about that. Similar to the peat problem, I think. Hopefully that's an adequate answer, an inadequate answer.
It's the best that could be done. Thanks.
Yeah, thanks.
Thank you all. Yeah, I think we already exceeded our planned time now, and I'm really grateful for your presentation. It's really useful for all of us. It was really fascinating, and a really big thank you for doing this, Tom.
Thank you, Tom.
And also, Pierre, to you for your participation and answers. At this point, I would just like to invite you to stay tuned and follow our social media for the future webinars. And of course, feel free to ask more questions in our forum as well. Thanks, everyone, and I hope to see you next time.
Yeah, thank you very much. Keep on sentinerding, everyone.
Thank you. Bye.
Bye. Bye.